Okay. Okay. Thank you very much, Mario. So, yeah. So I'll gonna try to go very slow and properly introduce the field of magic angle bilayer graphene and also the sort of emergent phases which we observed there, like superconductors, correlated insulators, orbital magnets, and topological states. And just to give a very slow introduction. So. Right. So first, let me also thank my group. So most of the work I'm going to talk about was done by a postdoc in my group, which is Xiaobo Lu, and a student Ipsita Das, and also Paul Seifert here. And I'm also very thankful for the collaborations we had, both experimental and theoretical. Most and foremost, Ellen McDonald, Andrei Bernovic, and Leonid Levitov, whose theoretical support was invaluable. And also we have collaborations with Eli Zeldov, Felix Baumberger, and Milan Allen, where we look more like on scanning probe and nano imaging techniques of our devices. Okay, and so basically just to start slowly, so the field of graphene is already pretty old, so it's like 15 years. And since the early days, people were trying to find some electronic interactions and more complicated phases in it. However, in the early days, most of the physics was just described as a single particle picture. And for example, I spent a considerable amount of time in my PhD to look at, to try to find superconductivity in graphene, but really there were a lot of predictions early on, but there was really no experimental progress. And this all changed dramatically when in 2018, where Pablo Carrillo Herrero side by side first discovered that in a certain type of graphene called twisted bilayer graphene, correlated insulators can appear. Immediately, he also showed that close to these correlated insulators, superconductivity appear. And then basically the discoveries kept on moving. So in 2019, then in the group of Goldhaber-Gordon, magnetism was demonstrated. And also this magnetism basically also gave rise to a robust topological stage, which was then observed by the Santa Barbara group. So, and basically now we really have all these phases in twisted bilayer graphene, all coexist often in a single device. So these phases can be gate tunable between one another in a very clean way. And we are right now basically at the stage where we try to understand how this can happen, how all these phases, what is the underlying physics of all these phases, what is the nature of superconductivity, what is the nature of magnetism and topology, and basically the field is really just beginning to take shape. Okay, so the outline of the talk. So I'm going to give a rather slow introduction about the sort of underlying physics, how these phases can be understood and how these phases can develop. So then I will talk mostly about my own group's work, which deals with really transport studies, where we were able to show the existence of all these phases. And last but not least, probably probably within an hour, I can also have enough time to touch base on that. Also, I want to talk about some applications, and these will basically deal with quantum sensors, in particular single photon detectors, where all of these two-dimensional superconductors can actually be very, very good materials for sensing applications. Okay, so just an introduction about van der Waals heterostructures. So basically, the field of graphene and van der Waals heterostructure is relatively old. And so it started really with the ability to extract two-dimensional layers from van der Waals materials. So for example, graphene can be extracted from bulk graphite in a very simple Scotch tape trick, but so can be a lot of other two-dimensional materials. And in principle, these materials cover any phenomenon in condensed matter. So we can have insulators, semiconductors, superconductors, magnets, etc., and so on. And so here is basically on the top is sort of a schematic of how we fabricate these devices. So we can start with exfoliating graphene on a silicon oxide substrate. So again, this is really a two-dimensional layer of graphite. And then we can what we can do is we can also assemble these layers into three-dimensional heterostructures. So basically, we can stamp other two-dimensional material species, in this case HBN. We can bring them into contact with this columnation technique. We can pick them up, they stick together, and we can repeat this trick all over again. So bottom line is we can really, starting from two-dimensional materials, we can stack up three-dimensional materials. And really, if you look at the cross-section of such a stack, it's really, you can combine any given sequence of different materials, and you can really combine, let's say, superconductors, Dirac metals, ferromagnets, and so on. And you can really sort of combine all of the properties of the different materials together. And while this initially we thought it's kind of wild that such a good, such a simple technique can actually give such amazing results, but really early experiments which studied, for example, cross sections with TEM microscopy of such van der Waals heterostructures found that actually the interfaces and the material quality can be extremely good and actually comparable to MB grown devices. And really here between HBN, graphene, and MOS2, very often you find regions where there are really no impurities. The interfaces are ultra clean, and you can you have a really you can hybridize the materials at the interface in a clean way over like a length scale of less than a nanometer. And then the other thing is, which is entirely new, which arises from this assembly of two-dimensional material, is of course the Moret superlattice, which will be central to the talk. So basically, since we assemble the materials one by one, starting from already pre-existing two-dimensional crystals, we can of course also choose freely the orientation between the crystals. And this is really, I want to contrast this to techniques which were developed previously to create heterostructures, such as molecular beam epitaxy, which was one of the most prominent techniques to build heterostructures starting from the 70s. So really there, because one starts with single atoms and one sprinkles atoms on surfaces, one has no control in the crystallographic orientation. So usually single atoms, they stick to the surface, they orient themselves on the given substrate, and they just inherit the crystallographic orientation from the parent material. Whereas really the ability that for van der Waals materials that where we don't start from single atoms, but we start from pre-existing crystallographic sheets, really allows us now to also orient them freely at a given crystallographic orientation. And this is really a dramatically new concept that works here. Okay, so starting with now bilayer graphene. So just want to run through what we do with and how the interesting properties of bilayer graphene develop. So usually we just start really with a single layer graphene. So again, this is this hexagonal hexagonal lattice of carbon atoms in 2 dimensions. And really, this sort of material is really well understood. So we really can just model it by sort of 2 atoms in a unit cell, A and B lattices, and a hopping term between these gamma 0. And if we do the tie binding calculation, and if we look at the low energy approximation of this tie binding calculation, we really get this linear dispersion relation, where we have basically where the electrons are basically described by this massless Dirac equation. And really, this is all basically well understood in graphene, and here really no interactions come into the play. And these Dirac cones here, which I'm showing, they are arranged in a hexagonal brilliant zone, and we have actually 2 values. So we have the K and K prime values. So whenever we deal with graphene, we always have to consider spin and valley symmetry. So usually graphene is 4-fold degenerate. Then what we can do, what was done for years, so we can just kind of consider double layer graphene. So again, when we just originally we could just exfoliate graphite, and then sometimes you also would find naturally occurring bilayer graphene, and this a stable form of bilayer graphene SIB stack. So this is basically where the top and bottom layer are slightly shifted with respect to one another. And so as you can see, so now, of course, the unit cell becomes a little bit more complicated. So we now have four electrons per unit cell. We have now additional hopping terms between the lattice sites, between the top and bottom lattice. And overall, basically, again, taking tight binding, taking a low energy approximation, we end up with 4 bands. And these bands are now not perfectly Dirac-like anymore, but they actually close to 0 energy. They become close to parabolic. So basically, they're described by a hyperbolic relation. And again, we have K and K prime valleys. And so all of this, of course, then kind of this whole picture kind of becomes much more complicated if we now take a second sheet of graphene and stack it with an arbitrary angle. So of course, we have now to consider many different things. So first of all, the Morel lattice is formed. So basically, there is an interference pattern between the top and bottom lattice. So these are really these bright regions here. The unit cell of this Moray graphene now becomes extremely large. So just to give an example, for approximately 1 degree twist angle between the layers, we have a unit cell which has around 10,000 carbon atoms. And the lattice constant becomes something in the order of 14 to 15 nanometers. So we have a Moray lattice here. The one way to think about the Morel lattice is that we can sort of assign regions of AA lattice sites and BA lattice sites, which periodically oscillate. And really, so AA lattice sites are the regions where the top and bottom layer basically overlap, and AB or BA regions are again these regions where the top and bottom are shifted. And if you can look at the topography here, you can see that this is really oscillating. These AA lattice sites have also a different height profile. And of course, electronically, we also have a mini formation of mini Brillouin zones. So now we have sort of mini Brillouin zones in the corners here, where we can think of the top and bottom Brillouin zone are twisted by the same twist angle as a real space, and we have these mini Brillouin zones forming. And overall, basically, because we now the hopping terms between the top and bottom layer are not well defined anymore, but they're periodically changing, then this leads also to strong reconstructions in the energy dispersion relation. And so just I want to demonstrate also some early experiments which we have done to sort of really characterize such systems. So for example, many groups, also our collaborators in Leiden, they were able to really map these Moray lattice sites with scanning tunneling microscopy. So really, this is just a height profile map performed by STM. And so you can see those bright spots periodically arranged. Those are not single atoms because the length scales is too large here. Those are really the AA lattice sites. So those are really the Moray structure which we can resolve. And this was, of course, done by many groups, including Caltech, Princeton, Columbia, and Rutgers, and many more by now. And the other thing is, as I mentioned, so the band structure becomes dramatically renormalized. And this is also something which was theoretically predicted. So you can see, so here's a theoretical prediction of a twisted bilayer graphene with a twist angle of 1.3 degrees. So you can see, so as compared to AB bilayer graphene, there is a huge reconstruction of the energy dispersion, resulting in isolated slant bands close to 0 energy. And also, of course, the Fermi surface becomes very complicated. And we were recently also able, in a paper together with Felix Baumberger, we were able to compare to reveal sort of this these flat bands and this structure with nano ARPIS experiments. Okay, and basically, as I will talk later on more about it, so the main sort of story here is really the formation of these flat bands. So in these flat bands, the density of states becomes extremely large. The kinetic energy of the electrons becomes extremely slow. So basically, what happens is that electrons basically stop moving. Your interaction energies become the dominant term in the Hamiltonian, and therefore interaction physics start to be the dominant sort of physics to consider here. Okay, so this is just like a theoretical introduction. So I want to move a little bit more to the transport experiments. So usually the devices which we are making are quadruple stacks of different van der Waals materials. So this is typical cross-section of a device which we're making. So usually we encapsulate twisted bilayer graphene in layers of HBN. So this is HBN is again just a two-dimensional insulator. And then we also have a graphite gate electrode exactly underneath it. And this graphite gate basically acts as a gate. So we can apply a voltage to the graphite, and it capacitively charges the twisted bilayer. So we can really by changing the voltage on the graphite gate, we can tune the electronic concentration in the graphene, and we can completely fill or completely empty the flat bands in the system. And this device image here shows a typical 4-terminal device which we make for our transport measurements. And I have to say that it was really a challenge to make homogeneous devices. So basically, the reason that is that if you think about the mechanical properties of graphene, the mechanical properties are really, if you want an analogy, is comparable to saran wrap. So it's really, graphene is a really stretchy, really flappery material. And basically, it really likes to form wrinkles. It likes to trap bubbles. And basically, the challenge here in terms of fabrication was that when you assemble two layers of graphene together, how do you create a process where you avoid wrinkles, where you avoid bubbles, where you avoid sort of air trapped between the layers? Because we found that really such imperfections can really dramatically affect the twist angle. And again, we want a homogeneous twist angle across the device, but if we get some trapped bubble somewhere in the device, of course, this distorts everything. So by now, we were able to make relatively homogeneous devices. Where the twist angle disorder in some cases reaches very low values of 0.1 degrees, 0.01 degrees over 10 micrometer scales. Okay, so now what we do in the measurements is really we measure just resistance as a function of carrier density. So we monitor the resistance in the device while we are sweeping the Fermi energy up and down across the flat band. And this is a typical measurement we're taking. So basically, we start a resistance measurement usually in the band insulator. So if I look at the band diagram where we have these flat bands here, usually we start our experiment where the Fermi energy is in this gap. And of course, there we observe really high resistance. This is where we observe this band insulator. And as you can see, so if we measure across the flat bands, the resistance changes dramatically depending on the exact filling, and it changes really by 10 orders of magnitude or something like that. And so here in the center, this is the charge neutrality point, which we sort of cross when the two bands here overlap. And then here, this is basically this other band gap which we fill up. But as you notice, besides the sort of features which are predicted by the single particle picture, which are basically these bands, there are many more other features which appear as resistance peaks at carrier densities which are equivalent to 1 electron per unit cell, to 2 electrons per unit cell, to 3 electrons per unit cell, and the same for holes. So there are clear resistance peaks whenever we have integer filling of electrons or holes per Moreau unit cell. And these peaks we cannot explain in a single particle picture, but these peaks we can explain as originating from electron-electron interactions. These we believe are correlated insulators. And the sort of physical picture in which we try to understand without going too much into the details, and really it's currently the picture of these insulators becomes much more complicated, taking also particular topological properties into account. But sort of the most naive picture how to start understanding these insulators is really in the multi-insulator picture in the Hubbard model, and basically where we assume lattice sites and hopping between lattice sites. So, and every electron has a kinetic energy term, which is sort of the hopping term, which allows an electron to hop from one lattice site to the other. And of course, we have the Coulomb energy or the on-site energy U, which is basically the Coulomb energy, Coulomb self-energy of the electron. So basically, if one electron sits at one lattice site, it costs much less energy if two electrons sit close by on an electron site. And so basically, all is good. So if the lattice is half empty, of course, electrons can just hop from neighboring sites in a next empty lattice site. But what happens if we are at exactly integer filling? So if we have all the lattice sites occupied with an integer number of electrons or holes, then what happens is that the Coulomb energy, if the Coulomb energy is too big, the energy cost to hop between neighboring sites is too big, and therefore the system becomes an insulator, and it forms an energy gap.
El código postal es 280047 de la Autónoma.
So, sorry, somebody's. I think somebody's speaking privately, right? Okay, no, I'll just continue. Okay, so and so basically, yeah. Okay, so basically, we end up in an insulator, which is basically just where the insulating gap is created just by electron-electron interactions. And because now we have fourfold degeneracy in the system, we have spin and valley. Of course, all kind of combinations of symmetry breakings are possible, which involve this SU4 symmetry of spin and valley. And we basically get insulating states at all the integer fillings and plus and minus 1, 2, 3 electrons per unit cell. Okay, the other thing is so these insulators we naively can understand in the following picture. The other thing is, of course, that we also found superconductors. So and for this, I'm showing this phase diagram, which is basically based on the same data, but now we have also plotted it against temperature. And again, it's just a resistance measurement. So again, red regions is high resistance, and blue regions is low resistance. And so the red regions again are these bent insulators here on the edges. So these are the normal the bent insulator gaps, and we have these correlated insulator gaps. So these are the red regions here and also here. And then, as you can see, so between many of those insulators, we also observe superconductors, which are dome-shaped, where basically superconductors, because resistance drops to 0, and it appears that the insulators are flanking. So, or in other words, the superconductors are trapped between insulator states, and they appear left and right between those states, depending on how you look at it. And so just wanted also to introduce, so the reason we are sure that these are superconductors is really because we did a lot of checks on these states. So first and foremost, of course, we measure critical temperature. So we measure resistance as a function of temperature, and we can assign a TC where really the resistance drops to 0. We can apply a perpendicular magnetic field, and we can see that the critical field as a function of temperature follows what is expected from the Ginzburg-Landau theory. We can measure nonlinear conductance, DVDI measurements, where we can extract a critical current, and we can also show that it follows a BKT transition. And for all of these things, we now have relatively consistent numbers between many different devices. So usually TC is in the order of 1 Kelvin. So sometimes it's 3 Kelvin, sometimes it's 5, but order of magnitude, it's 1 Kelvin. Critical field is around 100 millitesla. Critical current is around tens of nanoamps, and the coherence length is around 50 nanometers. But of course, the biggest sort of evidence at this point, which is really hard to explain otherwise, other than superconductivity, is of course the Fraunhofer interference pattern, which we observe. And we understand these as Josephson junction creation in the device whenever we have a disordered device superconducting in normal regions can separate from each other. There's phase separation in the device, and in certain instances, one gets these SNS junctions, which then give you this Fraunhofer interference pattern. Okay, so with this, so having established this, I want to also address the question of which really excited the whole community. So really, what is so special about this superconductivity? And really, so originally, there are many things which excited people. So first of all, it is the record lowest carrier density superconductor. So we have, in a recent paper, we have actually summarized many traditional superconductors as a function of thickness. So how thin can you make this material? And as a function of carrier density per sheet. And basically, so usual superconductors, I mean, normal BCS superconductors like aluminum or aluminum nitride, etc. Usually, it's really hard to make them thin. So it was a challenge for years to make thin films out of these, and even up to now, it's hard to make them thinner than 5 nanometers. And of course, because these materials are very good metals, the carrier density is really high, the Fermi temperature is really high. So carrier density per sheet are in the orders of 10 to the 14. Then there are other two-dimensional materials, also including high-temperature superconductors like BISCO. They're a little bit less. They're a little bit lower carrier density, and they are already quasi-two-dimensional. But really, if you can look at the position in the phase space where twisted bilayer graphene sits, it's really the thinnest material, but it's also orders of magnitude lower carrier density. So compared to high-temperature superconductors, there's like 3 orders of magnitude in terms of carrier density. And also, this was also part of the initial mystery. How can a material which has such a low carrier density still have a sizable TC? And really, if one compares really the critical temperature of the superconductor with the Fermi temperature, then one gets a ratio which is extremely high. So this ratio is really comparable only to high temperature superconductors. And then, of course, another thing which excited people is sort of this sort of superconductivity arising in a strongly correlated system. And of course, this immediately drew some debate whether this is a material which can be explained by a BCS theory, an electron phonon interaction, or maybe this is more like a material where electronic mechanism, purely electronic of superconductivity can be also exist. And of course, last but not least, the phase diagram, which naively looks very similar to the cuprates. So basically, if one looks at the phase diagram of the cuprates, where a multi-insulator upon doping becomes a superconductor, this sort of picture one can naively apply also to twisted bilayer. So this is sort of just a summary of the initial interest of superconductivity, but I also want to just quickly touch base. I think where are we now in this question? And so I think meanwhile, many groups, I mean, not many, I think 5 groups at this point have reported observation of superconductivity in twisted bilayer graphene. They have reported a number of devices, so really, it's not too many devices at this point, so statistics is still low, but I think we now have comfortably 10 to 15 devices between all the groups. And what is interesting is really that these devices at this point, they are rather, they show like a really slightly changing phase diagrams depending on which groups. And so basically these two upper graphs, they summarize a little bit this sort of narrative. Really, devices change a lot between for different twist angles, for different dielectric environments, etc. And sometimes we have observed superconductivity in the close to insulators. Sometimes we observe superconductivity without insulators. So I think I just want with this just to address key open questions. So which is the nature of superconductivity correlated insulators. Are they in competition, or is there like a mother-child relationship between those phases? Is there a similarity of cuprates, or do we need to really consider twisted bilayer as a completely independent systems? And I also want to address why I believe these phase diagrams alter so much. So first of all, I think we are still struggling to understand what are intrinsic effects and what are extrinsic effects, what are basically disorder dominated effects, and what are the robust quantum phases here. And here, one of the key challenges is twist angle control and homogeneity. So again, twist angle disorder can really complicate the observables. We have also all these things like twist angle disorder can also induce strain in the system. So we have a very rich strain profiles in the devices, which we need to consider. Then dielectric environment, as I will show in a second, is very important. And last but not least, I think we just need to get much more device statistics in the field. So 10 or 15 devices already getting there, but I think in a year or two, probably many other groups will get more statistics on this end, and we will develop a more robust picture. Okay, so for this, I want to also talk about the dielectric environment, which I mentioned here. So again, for this, to explain this, I just again want to go back to this naive Mott insulator picture. So again, in the Mott insulator picture, we have two terms, kinetic energy and on-site Coulomb energy. And actually, in twisted bilayer, we can control both of those terms. So first of all, we can control the kinetic energy by just changing the twist angle. So here is like a graph how the sort of band structure evolves, or the flatness of the band structure evolves, depending on twist angle. And of course, we have super flat bands at magic angle. But as you can see, if we move away slightly from exactly 1.1 degrees, the bands start to become a little wider, and then therefore the kinetic energy increases. And the other thing is really that our devices sit in a very complicated dielectric environment. So we have insulators, which have a certain dielectric constant, but we also have this graphite gate, which is a metal. And we can actually, as I will show in a second, we can also alter the dielectric environment and also affect the Coulomb energy. We can really dramatically change U, and therefore, in the system, we have a very good control over the U versus T ratio, which is finally the most important factor to consider the creation of a Mott insulator. Okay, so and really to control U, so what we did here is so we discussed with Leonid Levitov. So the theory is done by Leonid at MIT. And we really were wondering, so we have this graphite gate close by to the magic graphene. So how close do we need to make it in order to make screening effects large? So in order to screening affect U and to really weaken it. And the calculations here show that really, if we bring the graphite gate close enough to the graphene, where the characteristic length scales here is around 15 nanometers, then U can be dramatically weakened. So if the graphite gate is further away than 30 nanometers, U is basically unscreened. But sometimes somewhere around 50 nanometers, U becomes strongly weakened. And really, this is demonstrated sort of in this picture here. So the top demonstrates the magic angle graphene and the 1-year function. The 1-year function in graphene is extremely large. It's 15 nanometers, so it's really the size of a unit cell. And again, if we bring the graphite gate close enough to the 1-year function that it's closer to the 1-year function than its size, so again, closer than 15 nanometers, then really calculations show that the sort of screening in the graphite layer becomes relatively strong, and we can actually tune the interactions. And so we did the experiment with different devices. So we actually, for this experiment, we tuned both twist angle and dielectric thickness. So we we started with device D3 here, which is a dead-on twist magic angle, so it has the flattest band, and it has a dielectric thickness of around 50 nanometers. And then we basically measured a couple other devices which have twist angles which are slightly away from magic angle.
I think we've lost Dimitri.
Hello?
Yeah, Dimitri. Okay, we lost you for a bit. So like
for
20 seconds.
For 20 seconds, okay.
Yeah. 10 seconds, sorry.
10 seconds, okay, so I was, okay. Now it's okay?
Sure, it's really good,
okay,
yes.
Yeah. So basically what I was explaining is that we did the experiment where we controlled the twist angle. So we chose twist angles dead on magic angle and slightly away from it. So with this, we control T. And then we also chose different dielectric thicknesses. And so basically, device D3 shows by far the strongest correlated insulators. You can see this in these red regions, that's half filling, for example. So this filling factor 2, we see strong red regions here, those are strong insulators. But you can see, so when we look at device D2, on the whole side here, it doesn't show any more this correlated insulator, so this is gone. And whereas on the whole side, there is a little bit of correlated insulators, but very weakly pronounced. And then in device D1, which again has sort of the least favorable conditions for a mod insulator, we don't see any signature of correlated insulators, neither on the electron or the whole side. And as you can see, so what's also interesting, so the insulators disappear, but then we kind of really still see the superconductors. So for example, here on the whole side, there's no insulator, but there's a superconductor. But then here, most dramatically on this device, we have a superconductor in the absence of an insulator, which kind of transitions across half filling freely. And then actually one can also make the sort of comparison with this device where there seems to be a larger superconductor developing, but it's kind of interrupted by an insulator. So of course, our findings, they demonstrate that indeed the insulators can be controlled with dielectric environment, but B, it also reveals a sort of independent view on what matters for the superconductors and what matters for the correlated insulators. And I think with this, I want also to say that I think we are early on in the understanding, so I don't think I would particularly choose any sides at this point in the debate, whether it's electron-photon mediated superconductivity or whether it's electronic mechanisms. But I think this is the type of experiments which will need to do more in the future to really find better conclusions. So the other thing I want to say is actually want to talk about is actually about the topological aspects of twisted bilayer graphene. So we just had a paper on arXiv very recently, but actually some of those signatures we were observing already early on, and basically we observe what happens is we also have a very interesting phase diagram in twisted bilayer in high magnetic field. So what we started observing in some of our devices is that we observe like a very rich sequence of quantized Hall states at very, very low field, which cannot be explained just by Landau level quantization. So usually a Landau level quantization we observe at like elevated magnetic fields around 4 Tesla. But here, in a number of devices, we start observing quantized Hall states as low fields as 0.3 Tesla. And actually, in a recent device, we also observe it at 0 field. And sort of the typical measurement we take is, again, we measure RxX and RxY as a function of filling factor and as a function of magnetic field. And as you can see, so for this device here, we observe really a number of quantized Hall states where the slope in the B versus N phase diagram corresponds to a Chern number of 4. When we look at the state originating from charge neutrality, we observe a state of Chern number 3 for a state originating from filling factor 1, Chern number 2 from filling factor 2, Chern number 1 from filling factor 3. And all these states are well quantized. So if I look at sort of, if I take a cross section here and to measure RxY, this is this sort of map here, you can see sort of that really, so this is sigma xy is perfectly quantized. So these states really have a very robust sequence where a specific Chern number can be assigned to a specific carrier density, or to a specific filling factor. And we have summarized sort of many devices, so a total of 4 to 5 devices now. And we have basically put them in a single phase diagram. And really, these features really are relatively robust. So we really observe at a relatively low fields, Chern insulators originating close to 0 field from a filling factor 0. So from charge neutrality, so they have always a Chern number 4. And again, from filling factor 1, it's Chern number 3, 2, 1, and so on. So these are really findings. They were now also confirmed by many other groups. So these findings were confirmed by the group of Ali Yazdani, by Eva Andre, by Andrea Young as well, also by Pablo Ferredo Guerrero. They have observed these states, and sort of without going too much into detail. So the underlying understanding is now that the flat bands itself, they have a non-trivial topology, which is typically degenerate. So we can sort of understand the system as consisting of spin and valley polarized bands, which also have different Chern numbers plus or minus 1. And basically, depending now on the exact sequence of filling, we can polarize these bands in magnetic field, and we can really reveal the topological properties of them. And so I will talk, I probably don't have time to go too much into detail here, but basically these Chern insulators, we now understand as having their origin by breaking the valley and spin symmetry in the system. These bands have non-trivial barrier curvature, which causes orbital states. And of course, in reverse, these states have also non-zero orbital magnetization. So these states can be also explained as having being orbital ferromagnetic states. And again, there's a lot of work done on similar systems by many groups by now. So again, also David Goldhaber Gordon and Andrea Young in Santa Barbara. Okay, so with this, I think I will slowly start to wrap up. So I think I just want to summarize a little bit sort of our current view of this field. And then I will also spend another 5 minutes to go over applications. So, and really to summarize this, I think we're all very excited by the endless possibilities of marine materials. So we have observed really extremely rich physics, which involves correlated insulators, superconductivity, magnetism, topology. All of this is really in a clean system, which is gate tunable and where all these phases can be controlled and tuned from one to another, either by electric field effect or by magnetic fields. Really, I concentrated mostly on twisted bilayer graphene, but then, of course, there are now other groups who have looked at ever more complicated systems, such as, for example, aligning twisted bilayer graphene on HBN allows to break C2 symmetry, and then it also kind of gives you an entirely different electronic band structure and also phenomenology. Some groups have now also moved on to ABC trilayer graphene, which inherently has already flat bands, but also, of course, if you align them HBN, this can lead to very interesting correlated insulator features. Also, some groups, in particular Correlated, they have also used other materials to show that these flat bands can be created by twisting, for example, WSC2 and MOS2, which are semiconductors. And basically, I think we will more and more see in the next years that people start using many other materials. Again, semiconductors and direct metals are not the only things one can twist. One can twist superconductors, magnets. And I think overall, I think I'm really excited to see that this new universal concept will be used to discover new quantum phases. And again, I guess the main goal is really to try to find materials or combinations where the interactions energy can become ever stronger. So where U and TC and all these parameters can be boosted. Okay, so last but not least, I want to talk really also demonstrate some of the applications of it. So really, we realized already a long time ago, this was even before magic graphene was discovered, we realized that graphene in combination with superconductivity can be a really promising sensor for photons in particular. And it can be it can be a good sensor because it has ultra low heat capacity. So most sensors for quantum applications are thermal. So they use the thermal properties of a material or a superconductor to detect light quanta. And so graphene, if one does the calculations, graphene has a record low heat capacity, and therefore it is really sensitive to long wavelength radiation. So even gigahertz or terahertz photons can heat up the graphene electrons by a lot. And so here we were mostly sort of motivated by already existing superconducting single photon detectors. This is a company which we collaborate with, Single Quantum. So what they do is they make nanopattern superconducting thin films, which then can absorb. So basically, these consist out of around 10 nanometer thin spotted superconductors like niobium, and these are thermal detectors where, by absorbing a photon, you can drive the superconductor locally into a normal state, and therefore you can create a detectable signal. So when thinking just of this type of already existing technology, we realized really, again, looking at the comparison chart, that twisted bilayer could be extremely advantageous. So again, this low carrier density, which we have in graphene, which is again orders of magnitude lower than the materials which are used in these detectors here, also leads to extremely low heat capacity. So really, if one looks, I mean, we did the calculation in this paper here. If one looks at the heat capacity of magic graphene, it's really orders and orders of magnitude lower than in traditional superconductors, and therefore it is a much more sensitive detector material. And we proposed sort of this material to extend the operation of such superconducting detectors to really long wavelengths. So we propose that this technology can be extended towards the mid-hour, towards the terahertz, and even towards the gigahertz if one uses superconducting graphene. And I will not go too much into detail here. We actually, before even graphene became superconducting, we did already an experiment with proximatized graphene Josephson junctions. So again, the ingredient graphene plus superconductivity was here already in place. This paper just appeared in Nature 2 weeks ago. And so basically what we did here is we proximatized a graphene sheet. So this is here the Josephson junction, which we can see here. We can run a superconducting current across the Josephson junction. So this is basically the IV characteristics, which you can see here. And we found we basically used the critical current as a function of temperature as the thermometer in the system. So as you can see, so the critical current changes as a function of temperature. And this is really the thermometry we can do here. And at the same time, we integrated this graphene JJ into a quarter wave plate resonator for gigahertz photons. So this is really just superconducting circuit if you want. And we were able to basically guide single gigahertz photons into the graphene and therefore dissipate these gigahertz photon over it. And so without going into details, so we did the experiment, and really the detector performance which we got, in other words, the noise equivalent power which we got was in the attowatts per square root hertz, and transferring this ultra low number of the NEP into photons, it corresponds to 100 photons per square root hertz. It also corresponds to the sensitivity of a single photon of 32 gigahertz. Because this detector is integrated in a resonator, we have a quantum efficiency of 99%. And actually, this will be next week on Archive. We also have demonstrated that we can use such a device as a click detector, so we really can start counting single photons with it. So, and I think really this is also, in terms of applications, a really promising avenue, where really besides the rich practical applications. With this, I really want, again, to thank my group. I will also want to thank all my collaborators, and I want to thank you for your attention.
Thank you, Dimitri. Thank you so much for this really enlightening talk.
Thank you, Dima.
Hi.
Hi. So this quantum Hall transition, it's very, very weak magnetic field. This is breathtaking. So what happens at charge neutrality? What you believe happens in the limit of zero magnetic field is jump from -4 to +4 at the point of charge neutrality. And it's a what gives this 8 units of quantized Hall connectivity?
Right. So okay. So I think I'll be quite honest. I'm still trying to read up on Andrei Bernovik's 6 papers. So I'm still working my way through the theory. So there were a lot of complicated theory papers out there recently. So I think, as I understand, the ground state which one possibly can get is degenerate, so one can get 0, 2, and 4 Chern numbers. I think we definitely sometimes see a gap at charge neutrality. So maybe this is a Chern number 0 state, and we definitely sometimes see well-pronounced Chern number 2 states too. So I think we're still not 100% sure, you know. So because the thing is, at one point at higher field, we also start observing Landau levels. So we really, to distinguish what is Chern insulator here, what is Landau levels, we need to be careful and try to look at what happens at the lowest fields. So we sometimes do see 0 and 2, which is also relatively strong.
Maybe I can ask.
And just one quick question. Do you see hysteresis?
Yeah. So we see hysteresis. So actually, we also see some of those features at 0 field now, and so basically, yeah, there is hysteresis. Yeah.
I see. Eli, I was stopping you. Sorry.
Yeah, no, I wanted to answer your question. So the answer is yes. You see 8-fold degeneracy jump from -4 to +4 at very low
charge
field.
neutrality.
At charge neutrality.
I see.
Yeah, I'll show it in my talk, but that's we see it clearly at low fields.
I see.
Okay, Adi, thank you so much. We have a following question from Mario Cuoco.
So can you hear me? Hi.
Yep.
Yeah. Hi. So thanks a lot for a nice talk. So I have a question about the energy scale of your charge gap in the insulating phase. What is controlling this charge gap? How much is it? And so whether you can really single out fingerprints of mode physics in the behavior as a function of density or other whatever, other parameters you can change.
Right. So okay. So this is a little bit more quantitative view on the gaps. So basically, yeah. So the gaps are relatively small. They're below 1 MeV. Usually the strongest insulators we observe are churn number, is filling factor 2 or -2. And sometimes we also see a charge neutrality, a relatively large gap in the order of 1 or 2 MeV. But okay, so this is quantitative. So the way we extract those gaps is just by temperature activated transport. So we just measure resistance as a function of temperature, and then these insulators manifest themselves as exponentially increasing resistance at low temperature. But your question was how do we know it's MOT insulators, or?
Yeah, I mean, since it's so small, I mean, where you find, I mean, so how you can judge that the Coulomb interaction is really gapping out your electronic system and is not any other whatever mechanism which can produce this tiny gap. I mean, it's so this is my question. Whether, I mean, so where is whether in the experiments you have some evidence of other, I mean, features, I mean, above the gap that can show this effect of the Coulomb interaction somehow.
I mean, right. So you know, so I think. So so I agree with you that the gaps are not so big. So, you know, this is mainly due to, so I think, you know, if you would, so the difference between twisted bilayer and normal MOT insulators like the cuprates is that we have a much larger unit cell here. So in a crystal system, interaction energies are much bigger, and therefore the temperatures are much bigger at which the gaps form. Because the spacing, I mean, the units, the lattice constant are very small. So here we have an order of magnitude bigger lattice constant. So if you look at the expected interaction energies and energy gaps, they're really not that large. They are expected to be much smaller. And then right. So and then our sort of the biggest evidence is really that those have insulating behavior, and those appear at exactly integer fillings of carrier density, and then the rest is theory, you know.
Okay, thanks a lot.
Thanks, Mario. We have more questions. Ilya Eremin, please.
Hi, Dimitri. Very nice talk. I have a question regarding basically the small carrier density that you have in the superconducting state. So do you see any signature of pseudo gap behavior? Because I would expect some you know, BCS, BEC type of physics.
Right. Yeah. Right. No, I mean, so this, okay. No, okay. So I'll no. Okay. So we don't see it. No. We don't see it, and then I was actually sorry about jumping around. I was just trying to find some slide, but no. Yeah, so no, we don't see it. Honestly, like I think I once discussed with people who remember how the pseudo gap was found in the cuprates. This was found like 10 years ago, and those were very finicky, very fragile signatures, which revealed this energy gap. So I think we don't see those signatures, but maybe we're just overwhelmed with the richness of the phase diagram in general. So I don't think we are at this point yet where we can really convincingly can find weak features like that, I think. Okay. But no, nobody has observed, nobody has reported anything like that.